Hello, and welcome to the Dr. Kaboomski channel. Today, we're exploring the enigmatic and captivating realm of neutron stars. These cosmic bodies are remarkable marvels of the universe, but what exactly are they? How do they come into existence? And what purpose do they serve in the universe? Stick with us to uncover all there is to know about neutron stars. To understand what a neutron star is, it's crucial to know its beginning. It's crucial to know the origin of a neutron star to comprehend what it is. Neutron stars are created from the leftover pieces of a supernova, which is a violent explosion of a massive star at the end of its life. In this explosion, gas and dust are thrown into space, while the core of the star collapses because of gravity. Formation. This collapse is happening very quickly. Matter falls so fast that electrons and protons come together to create neutrons. That's why they call it a neutron star. These neutrons are incredibly compact. In theory, a small amount of material from a neutron star would weigh billions of tons on Earth if you put it on a teaspoon. It's hard to imagine how dense these objects are. Size and density. Typically, their mass ranges from 1.42 to 0.1 times that of the Sun, while their diameter is usually between 10 and 20 kilometers. This means that they are very compact, with an average compactness similar to that of an atom's nucleus. Neutron stars vs. black holes. Neutron stars and black holes are different. Remember to differentiate between neutron stars and black holes. When a massive star collapses, it forms a neutron star, but if the collapse is more extreme, it creates a black hole. Black holes have a singularity where the laws of physics we know no longer apply. Fast rotation. Neutron stars have an intriguing feature: their rapid spinning. Another captivating feature of neutron stars is their rapid rotation. When a massive star disintegrates and forms a neutron star, the conservation of momentum causes this rotation to be exceedingly swift. Certain neutron stars can orbit hundreds of times in 1 second, making them very enduring and suitable for specific astrophysical uses. Detection. Finding neutron stars can be difficult because they're small and dark, but we can locate them by looking for their effects on the environment. Their strong gravity can affect nearby stars, and their quick spinning can create radiation emissions that can be detected with telescopes. Formation of neutron stars. Neutron stars are created by a chain of magnificent cosmic events that start with the stunning blast of a big star nearing the end of its life, which is named a supernova. During a supernova event, gas and dust are expelled into space while the star's core collapses due to gravity. As a result, a neutron star begins to take shape. The star's material becomes increasingly dense, causing electrons and protons to merge, creating neutrons. Supernova explosion. A supernova is a powerful event that happens in space. When a very big star dies, it uses up all its fuel and its core collapses. This collapse causes a lot of energy to be released in the form of heat and light, causing a big explosion. Nucleosynthesis. Elements heavier than iron, like gold, lead, and platinum are created through nucleosynthesis during the explosion. This process means neutron stars are crucial in forming heavy elements discovered on Earth. Rapid collapse. Collapse happens quickly. Matter falls fast, which makes electrons and protons combine to create neutrons. These stars are known as neutron stars because they are so densely packed with neutrons. As a result, they are intensely heavy with strong gravity. Unbelievable density. Neutron stars are incredibly dense, with even a tiny amount of material weighing billions of tons on Earth. This density is due to the rapid collapse of a massive star, where protons and electrons fuse to create neutrons. Intense gravity. The gravity on a neutron star's surface is super strong because it is very big but tiny. If you stood on a neutron star, you would feel a force of gravity billions of times stronger than on Earth. The gravity on a neutron star's surface is super strong because it is very big but tiny. Therefore, people cannot explore neutron stars. When discussing neutron stars, one can easily be captivated by the world of science fiction. Just envision a tiny amount of substance that weighs billions of tons on Earth due to the force of gravity and its high speed of rotation. These elements raise an intriguing question. Could exotic life exist in neutron stars? Are the extreme conditions of these celestial objects able to facilitate familiar forms of life? Or do we need to envision something entirely new? Share your theories and speculations in the comments section below. We're eager to read your ideas. Don't forget to like and subscribe to the channel so you don't miss any videos. Powerful magnetism. Neutron stars have an extremely strong magnetic field. That's billions of times more powerful than the Earth's. This generates various occurrences, like neutron pulsar stars, pulsar neutron stars. Neutron stars, known as pulsars, spin quickly and broadcast radiation beams. When these beams intersect our view, we detect consistent signals resembling a space lattice. Pulsars are valuable space-time keepers and have aided meticulous astronomical studies. Intense heat. Despite their small size, neutron stars are extremely hot on their surfaces. Their temperature can exceed 1 million degrees Celsius. The intense heat results mainly from the initial collapse of the massive star, which compresses matter, generating heat. Radiation emission. Neutron stars give off different kinds of radiation, like X-rays and gamma rays. Their powerful magnetic field and fast rotation cause these radiation emissions. Special telescopes are used by scientists to analyze these signals and understand more about these enigmatic entities. Practical applications. Neutron stars are useful for astrophysics research, including experiments on Einstein's general relativity, high-energy physics, and the properties of matter at very high densities. Their strong magnetic fields can also help us understand magnetic phenomena in space. Production of heavy elements. Neutron stars are crucial for producing heavy elements. When a supernova happens, it creates intense conditions that enable the formation of elements heavier than iron. These elements, like gold, platinum, and uranium, spread all over the universe and serve as the foundation for building planets and solar systems, including ours. Study of matter at extreme densities. Neutron stars let us study matter at very high densities, far greater than what's found on Earth. This helps us explore fundamental physics and understand how matter behaves under extreme conditions. Equations of state of matter at high densities are crucial for understanding supernovae and neutron stars. Understanding the nature of pulsars. Pulsar neutron stars are great things to study. They spin fast and send out beams of energy. They move in a predictable way, which helps scientists make important discoveries about space. For instance, scientists have found planets outside our solar system and learned more about dark matter by studying pulsars. They even confirmed some ideas about how the universe works. Practical importance. The significance of neutron stars exceeds academic purposes. Neutron stars' powerful magnetic fields have real-world effects on human technology. For example, data storage and navigation techniques. Comprehending the physics of neutron stars can enhance our daily technologies. Neutron stars are one-of-a-kind space objects with super high density, strong gravity, strong magnetism, high temperature, and captivating radiation emissions. Learning about them is very important for understanding the universe and has meaningful practical applications in astrophysics. Thank you for watching the video. If you have any questions or comments, please leave them below. Remember to subscribe to our channel for additional content about scientific facts, the universe, and astrophysics. See you next time.